All right, so now we're going to pick it up where we left off the other day, talking about black scholes. So we were basically introducing the model and talking about the statistical underpinnings of the model. And so I was using this document, Black Scholes Assumptions, to cover some of the details that are going on behind the scenes. And then now it turns out, though, I must start by saying that I made a really dumb mistake last time. And what is that dumb mistake? It had to do with the normal distribution, where I mentioned probabilities that would turn out to be not correct. And so the way it works with the normal distribution is that you drew the curve. Here's the center. Remember, the distribution is symmetrical, so it should be identical on either side of the mean. So what you're seeing here, oops, sorry, what did I do? This area that I'm shading in represents the probability of being within one standard deviation of the mean. In other words, anywhere from one standard deviation below to one standard deviation above. And so we'll see when we go into Excel that this is approximately 68.26%. And so I think I inadvertently said 3413, which would be half of this, but it is actually 68.26. And then if you move out to two standard deviations, and then I guess we could shade that with a different color. That brings us up to about 95, let's say 44. Okay, so those are two things. You don't have to memorize those, but it's good. It gives you a feel for how this curve, or what are some of the key properties of this normal curve. Another thing that I just want to remind you too is that the curve itself goes up to infinity on the upside and all the way down to negative infinity. And the total area under this curve is equal to 1, which represents 100%. Okay, let's see. I'll sneak it in down here. So 1 is the same thing as 100%, just like up here, 68.6286 is the same thing as 68.26%. The area under the whole curve is 1. And due to the symmetry of the distribution, the area above the mean is half of that, and the area below the mean is again 0.5, 15%. That's the only way that the curve can be symmetrical and still have a total area of 1. Now, what we're going to see is in Excel how to calculate any probability we need. Now, these are in between probabilities. Sometimes we'll need the probability being below a certain point and above a certain point. And so we'll get to that in a bit. One more thing I do want to mention here is that there can be an infinite number, or I should say there is an infinite number of normal distributions, each with a unique mean and standard deviation. There's one that's particularly useful in many applications. The normal distribution with a mean of 0 and a standard deviation of 1 is known as the standard normal distribution. Also, incidentally, we usually use the letter Z to represent a standard normal random variable, whereas the others are typically represented with an X. Okay, so that's a point of notation that you'll see as we go along, because the reason why I'm bringing this up now is because in the Black-Scholes formula, we're actually using the standard normal distribution. Okay. So anyway, the next thing we wanted to consider is this notion of volatility, which is a critically important part of this model. Turns out to be really one of the more important determinants of the value of an option. And so that's represented by the sigma, which is the standard deviation. Sigma squared is the variance, but sigma is what we mean by volatility. So specifically what it refers to is this. Okay, now what we're actually considering is not the prices of the asset underlying the option, but the returns. Okay, so in other words, if this option is written on Apple stock, that S represents the price of the Apple stock, but um, the volatility is based on the returns to the Apple stock. So the returns can be calculated in one of two different ways. And that depends on our compounding assumptions. So a rate of interest can be compounded in many different ways. For example, annual, compounding, semi-annual compounding. We can have quarterly compounding. We can have monthly compounding. We can have daily compounding. And what does this mean? It means that with annual compounding, whatever the annual rate of interest is what you earn once a year. With semi-annual, the annual rate is basically cut in half and credited to your account twice a year. So, for example, if the annual rate of return, or I guess what I should say is the annual rate of interest is 6%, then with semi-annual compounding, the investor is credited with 3% twice each year. With quarterly compounding, investor is credited with 1.5% every quarter or 4 times per year. So all of these cases, now, by the way, in practice, when you take your money to the bank, chances are pretty good they're giving you daily compounding. That's the standard with banking in the US. But for certain types of securities, you may run across these other compounding conventions. All of these are collectively known as discrete compounding. And so with discrete compounding, the rate of return is actually calculated. Let me add this in here. And it's a very simple idea. All you're doing is taking the percentage difference in the price you paid for an asset and what you sold it for. Okay, so in other words, here we're using the convention PT plus 1 is the price. Actually, I'll tell you what, let's start with T. T is the price at time T, where we usually let 0 represent today. Okay, so in other words, if I buy the stock right now today, I'll call that time 0 typically. And then PT plus 1 would be one period in the future, which could be a year, but it doesn't have to be. Okay, so that depends on the situation you're in. It could be an annual change, it could be a weekly change, whatever the case may be. So when you put it into this form, got here is the percentage change in the price of the asset. Okay. So that's what the rate of return is actually telling us. Now, for quarterly compounding, then of course these time periods would be quarterly. For semi-annual, these periods would be semi-annual periods. Now, when you reach the limiting case, though, if you notice, we have progressively more compounding periods. And so, like for example, daily compounding is means that this return is compounded 365 days a year. You can see that as we increase that, we're approaching a limit, as it turns out. And so the limit of compounding frequencies, where the number of compounding periods per year is infinite, is known as continuous compounding. So that's this assumption we'll often make, you'll find in derivatives models. There's a lot of reasons for doing this. It has some very helpful mathematical properties, continuously compounded rates of return compared to discrete rates of return, where there are inaccuracies introduced over, especially if you're looking at a return over a long period of time. But so this is what we'll be using, at least with the Black-Scholes model, and probably through the rest of all the models we'll be looking at. So when we have continuous compounding, we change the way we calculate the rate of return. Now here, just keep in mind, actually, we could have done this in two different ways. I just thought of this now. Sometimes, let's go back and revisit this one. In some books, they write the rate of return like this. Okay. Where it's understood that we bought the asset at time t and we sold it at time t plus 1. Okay. But sometimes what you'll see is this instead. You can see it's the same thing. It's just that you're thinking of t as the time which you sell the asset, and t minus 1 is the previous period when you bought it. So it gives us the same thing. It's a percentage change, but every book is a little bit different. Now, Hull's book usually does it this way. And so with continuous compounding, instead of calculating the percentage difference, you're calculating the log, natural log, of the ratio of the selling price over the purchase price of this asset. Okay. Right here. So now, of course, what you're seeing here, you're actually taking the limit of this expression as the time between t and t minus 1 approaches 0. Okay. So that's what this is all about. So if, for example, if an investor buys a stock for let's say 100, and sells it for 110, continuously compounded, this a year later, let's say. So it's just a natural log of 110 over 100. And let me get out my calculator. Now it's going to give you a number that you might not be expecting. You would think it would be 10%, but actually it is not. Oh, I just realized I left out the -1. You have to subtract 1 because that represents the original principal. So, well, actually, no, you don't. Sorry, not with this one. Never mind. This one, yes. Actually, that's right. I just realized I left it out. It's like here, for example, actually, let's do both examples side by side. An investor buys a stock for 100 and sells it a year later. Let's do the discrete return first. Okay, so for this one, you would have it's 10%. It's exactly what you would have thought. Here, though, what you're going to have instead is 0.0953 or 9.53%. Now, it may not seem like it, but earning a 10% return on an annual basis and a 9.53% return with continuous compounding represent the same information. Okay. Now, in a way, it's kind of like the difference between Celsius and Fahrenheit. But the reason why this is happening is because if you use these numbers to calculate the future value of your investment, in the first place, so you have 100, let's say $100. You have a 10% rate of return. N is the compounding frequency, which in this case is 1. And let's again assume it's an annual investment, 1-year investment. Okay. Just to keep it simple, you'll end up with $110. Now, we already know that the person who invested bought this asset for 100 and sold it for 110. So the 10% means that you earn 10% of your original investment at the end of the year, so that the future value is $110. With the continuous compounding, though, the future value, if you recall, is equal to so if you pop that into your calculator, oops. Okay, so except for the rounding, you're going to end up it's like 109,999 something. It's 110. It's only off by rounding. Okay, in other words, that 0953 is not exactly correct, but you're getting the same future value. So in other words, when you change the compounding convention, um, you're not changing the future value of your investment or the present value. What you're changing is the way the rate of interest is calculated. But you can see here that the two numbers represent the same result, 10% on an annual basis, 9.53% on a continuously compounded basis. It ends up meaning the same thing. So in Hull's book and in many other books, they choose to use the continuously compounded rate of return because there are issues associated with discrete returns. Just as a quick example of this, why you would consider using the continuously compounded rates. Suppose an investor buys a stock for 100. At the end of 1 year, stock price falls to 90. At the end of 2 years, the price returns to 100. Okay, now here's the tricky part. If I calculate the discretely compounded, the annually compounded rate of return, watch what happens. So the first year, we lose 10%. Year two, gain 11.11%. And so if you add those together, oh, for God's sake, it appears that you've made money, but you haven't. You just broke even. But if you use continuously compounded returns, watch what happens. So the log of 90 over 100, 9, no, sorry, the log of 0.9 is about negative 10, 10.53%. Two, with a natural log of 100 over 90, which is positive 10.53. And the total is 0, which is what it should be. So the discretely compounded rates, there can be a bias when you calculate long-term returns. With continuous compounding, that doesn't happen. So with discrete returns, you can have a bias built into the calculation of long-term rates of return, whereas with the continuously compounded returns, you don't run into this. That's one of the reasons why for the modeling we'll be doing, it's easier to deal with continuous compounded rates, even though in practice you don't see that very often. No bank out there is going to offer you a continuously compounded rate of return. But you can convert any convention into any other one. Okay. All right. So that's that. But the volatility, so the reason why this is all relevant now, because the volatility is based on the standard deviation of the continuously compounded rate of return. Okay, that's why this is relevant. All right, and we'll see that when we do the calculations for Black-Scholes. You may be given the volatility, but you might also be asked to do it. If you're given a time series of stock prices, you could do it yourself by calculating the continuously compounded rates of return, and then you would go ahead and calculate the standard deviation of that time series of returns. Well, all right then. So yeah, see, the unfortunate thing about the drawing that I'm doing here is that if you aren't careful, it can get distorted very quickly and easily. Those little drawings tend to slide around when you change the text. So we have to be a little careful here. All right, I think we're all set here. Now, let's go back to the Black-Scholes and let's see what else we have to explain. So now we understand what the volatility is. It's the standard deviation of the continuously compounded rate of return to this asset S. By the way, if asset S provides some kind of a cash flow to the owner, we have to approach this a little bit differently. But here we're assuming that remember, this is a stock that does not provide any dividends. So we don't have to deal with it right now. All right, what else needs to be explained here? N of X is, okay, the cumulative normal distribution. What is that all about? Okay, well, let's take a look at this curve. So we have, as we've seen before, the standard normal. And the way we calculate probabilities, for example, here, the probability being between A and B, is the integral of the function, which I haven't showed you yet. It's in the slides. The formula that is being used to generate this normal curve. I guess I could slip it in here somewhere because we don't actually need to write it ourselves, but it might be nice to know how that works. It's because it's built into both VBA and Excel. So for the normal distribution, the function that assigns probabilities, in other words, the curve represents what I'm about to draw here. I have to be a little careful here. Let me make it a little bigger. Okay, so this is pi, the actual pi that you know from high school geometry, 3.141, etc. And if you notice, the x represents whatever variable we're looking at. The mu and the sigma are the mean and standard deviation of this normal distribution. So a while back, we drew some curves to show you how these affect the shapes of these curves. Let's just go back and revisit that for a second. Oh, maybe it wasn't this document. All right, that's all right. We can do it right now as a quick review. Okay, let's try that. So just a quick reminder that when we're looking at the normal distribution, the mean determines the location of the distribution on the real number line. So you can see that these two have the same standard deviations, have the exact same shape, but they are located at different points on the normal curve. And then if we only change the standard deviation, then it's the shape that's different, but not the location. All right, well, that's not perfect, but we try that one more time. The peak of the curve is supposed to be in the exact center. That's not so bad. All right, so this one, the mean is the same, but man, that standard deviation is big. Okay. So that's why it's so spread out. So if these represent the rates of return to two different stocks, then this lower, flatter curve is much riskier than the taller curve. Okay, because the returns are spread out all over the place. There might be some years where you have huge positive rates of return and other years where you have huge negative rates of return. So anyway, the point of all this is that the mean and the standard deviation uniquely characterize the normal distribution. If you know those two things, you know everything you need to know about that curve. Okay, it tells you the shape, the location, and it also will determine the probabilities for any given values. By the way, so these are sometimes called the parameters of the distribution, meaning that those are the ones that characterize its behavior. Um, if you've had any statistical background, you know that there's many other probability distributions, and each one has its own unique set of parameters, anywhere from one to many. Um, it depends. You might recall the Poisson distribution, for example. It has one parameter called lambda, and there's some very complicated functions, distributions rather, that can have two, three, four, five, any number of these parameters. But you can see, because this formula is telling us that the calculations depend on the constant pi, x itself, whichever variable we choose, whatever its location is under the curve, and then the two constants mu and sigma, and of course here's e. So it's the mu and the standard deviation that are really uniquely determining the results of calculating normal probabilities. Now, for the standard normal case, uh, it's only slightly different. The only difference is that we have a mean of 0 and a standard deviation. So the formula, and also don't forget, we're using z's instead of x's. Okay. So this time it'll look like this. Oops, you know what? I just realized I left out the square up here. Sorry about that. There's supposed to be a square here. I'm sorry, I forgot that. It's -1/2 x minus mu over sigma squared. All right, so here it's going to be z over 2 squared. Now, if you notice, it appears that we've lost mu and sigma. We haven't. Z itself could be thought of as this ratio. And then down here, the sigma is 1, so we don't need it. And it just means that when you draw it, the center is 0. And then that means that being one standard deviation above the mean is equal to 1. And so it's often very useful to work with a standard normal distribution, because the values that we're calculating are easy to interpret in terms of standard deviations from the mean. Okay. Now, Excel has functions to let us calculate these. Now, what is this building up to? These functions, as I mentioned before, these are referred to as probability density functions. They provide us with probabilities of being within a range of two values. Okay, so just as a quick example, actually, we've already seen this one. This is the one that I goofed up before. Probability of z being between these two values is 6826. Now, what we also have corresponding to this probability density function is called a cumulative function, shows the probability. The normal random variable is less than or equal to a given value. Like, for example, what if I want to know the probability that z is not between negative and positive 1? Something like this. Okay, well, because of the symmetry of the distribution, if the total area is 6826 between negative and positive 1, that means each of these two must be half of that. And so down here, that means this is 0.3413. And I mentioned the other day that the area below the mean equals a half. So this probability adds up to 0.8413. So there's a function that will calculate this directly for us. And when you see this function, um, it's usually written slightly differently. We start by using capital F to indicate this is the cumulative distribution function, which means it's a less than or equal to probability. And what you're actually doing here is integrating that function from 1 down to negative infinity. So the actual formula for this, I don't think there is actually. If there is one, we don't really need it, because all we need to know is that we're integrating the probability density function over the range from negative infinity up to whatever value we need. And that integral will give us the appropriate probability. Okay. So that is what these in this Black-Scholes formula. The reason why this is relevant is because when you look at this Black-Scholes formula, these n's are the cumulative probability distribution functions. So in other words, when you see n of x, it means let's think of this as capital X is the random variable. This lowercase x is the specific value that we're looking for, like 1 in my example I just gave you. This is, by the way, how I draw lowercase x's. It's very difficult to make a distinction sometimes. Lowercase x, I just try to make it a little fancier. Um, it's the same thing with z's. It's very hard to show the distinction between the two. And this is a specific value of x. Hold on. Okay, so we want to make sure we know the distinction between the two. All right, anyway. So that's what those n's are doing there. And so they are cumulative probabilities, less than or equal to. So this ND1 means this is your standard normal curve. Here's your D1. N of D1 is this area. And for ND2, by the way, these can be positive or negative. Although they're more normally positive, but here, let's say this is your D2. And that's what this is for. Okay, so we're assuming that we're using the standard normal distribution. And so these n's are the cumulative probabilities based on that standard normal distribution. Okay. All right. So now I have wait a minute. Let's see if there's anything else that I covered in here. Oh, this is a drawing, which is an attempt to show you how the two are different. For less than or equal to 1, which is the one I just used a second ago, um, this is over here, the probability density function. Which is usually abbreviated PDF, of course. Over here is the corresponding cumulative distribution function, or CDF. If you notice on the right, the curve is representing the total area up to that point. Okay. So in other words, on the left, they're showing the height of the curve is the probability, but on the right, what you're showing is for the height of that curve is the cumulative probability, which means that it's converging to one. In other words, you can see right here, you can't go above one. The height of that curve cannot go above one. So the red area on the left for the less than or equal to 0 equals the red area on the right. And then for less than or equal to 1 is that black shaded region. And so on the left, the area is 0.85413. On the right, it's the height of the curve that's 8413. So on the right, we're looking at heights. On the left, we're looking at areas. So that's the distinction between the two. Oh, this is coming up later. This is the call parity condition. This is what we need to apply to the Black-Scholes formula. Once we know the price of a European call option, we can price the corresponding European put option with this special condition called the put call parity condition. And what's interesting about it is that it's a mathematical relationship that must hold. Otherwise, the otherwise is there will be an arbitrage opportunity. So this section is actually a proof, although it doesn't look like it. This is a proof that the put call parity condition is in fact an arbitrage-free condition. We're going to show what happens, not just yet though, when this put call parity condition is violated. And then we're going to look at the formula that is implied by this result. So what we're going to do now, I think it's time to take a look at Excel. Let's take this information, read it into Excel, and let's try to reproduce these results. Okay. And let's go in here. And you'll see the spreadsheet is called Pricing Options Examples. There's two of them, sheet 1 and sheet 2. So here we have a stock, which is $52. The strike price is 50. The risk-free rate is 2% per year. It's per year because this is a 1-year option, as you can see here. T is 1. And then this is our volatility, 30% per year. Volatilities are always quoted on an annual basis. And so what we're going to do, we're going to solve for the Black-Scholes formula in stages. And so what we're going to do first is solve for D1 and D2. Now, these formulas are kind of messy, especially D1, realistically, unless you're a complete beginner with Excel. Or even if you're not, I mean, no matter how much experience you have with Excel, is what I should say, you could easily make a mistake with this one. It's pretty messy. So we have to watch out for the parentheses. That's really the biggest challenge here. So what I'd like to do is do it in stages. Start with equals natural log. Excel spells natural log ln, which, by the way, VBA does not. We'll get to that in a bit, but VBA has a handful of functions of its own that we have to use, and it turns out that VBA chooses to spell natural log, L-O-G, for some reason. So right now, let's focus on Excel. We have S over X. R, the risk-free rate, plus 0.5 times. Now here at sigma, we have to square it. With Excel, you're using that caret character. That pointy thing is called a caret. So we shift 6 on your keyboard. We square it. Then all of this has to be multiplied by t. And now all of this should be enclosed in parentheses because this is the numerator. And then we're going to divide by, very simply, sigma times the square root of t. Which, by the way, again, square root is another one of those functions, and I'll give you a list of the ones that we need later on, but where it's spelled differently in VBA. All right, so that's what we expected to get. It's already been calculated here for you. D2 is easy because it's just D1 minus the square root of T. Oh, sorry, not square. What am I doing? Times, I've left out the volatility. That's better. Yeah, they're usually not that far apart. Then the ends. Now, this is where we start to need some specialized Excel knowledge. The function here that we need is called norm dot s dot dis, which stands for the cumulative probability taken from the standard normal distribution. So because you're telling Excel that it's the standard normal, you do not have to specify the mean and standard deviation. It understands that the mean is 0 and the standard deviation is 1. So you need to tell it the value you're looking for. So this one, I'm looking at D1. Now, there's an interesting value next to it called cumulative. What is that all about? Well, for our purposes, we're going to use the 1, which means yes. And by the way, you can see in here that that is what we were looking for. So if you drew a picture of this, which is equivalent to saying the probability that Z, the standard normal distribution, is less than or equal to 0.3474 is 0.6359. Now, cumulative. Why do they have this value there? Why are they asking? By the way, if you're not sure how a function works, you should use this little fx insert function. It'll explain to you what both of these terms mean. Cumulative, either it's yes or no. In Excel, you can put either true or 1 if it's yes, false or 0 if it's false. Putting a 1 there means you're actually looking for the cumulative distribution function. If not, what would happen? If you change that cumulative to 0, this is what you'll get. 0.3756, which is the height of the curve at that point. Okay. So that's not what we want, is it? It is not. But we'll see later on, we do need to use this function here for other applications. We don't want to ignore it. And so the notation that Hull uses in his book is this is written as n of d1, and this one is written as n prime of d1. Okay, so it has, we'll see later on what it really represents. Okay, it will be needed. Don't worry, we will need it. Now, these two are kind of optional because what they refer to is here's our put call parity condition. We can use this once we know the value of the corresponding European call. But it turns out there's a formula we can use that avoids the need to calculate the call price in the first place, but it needs these two numbers. So all you have to do, oh, you know what I forgot to do? I forgot about ND2. So remember, it's norm.s.dist of D2. Oh, I forgot. Oh, for God's sakes. Now, the funny thing about this is that for all these years, that cumulative was only added fairly recently. So it was all those years I was used to it only asking for the z-score or the value of the z or standard normal random variable. That cumulative thing, I keep forgetting about it because it's fairly new. Anyway, so for n of negative d1, d2, you just put norm.s.dist of negative d1. Oh, see, I did it again. It's like it's a force of a habit. Negative d2. Now the call is coming from here. So we've got almost everything we need. We've got S times ND1 rate. Now here we need X. Okay, what about e to the minus RT? How do we implement that in Excel? Well, e to the X in Excel is spelled EXP. And then you put in parentheses the exponent, which in this case is minus R times T. And then you still need N of D2. Oh, what did I do? B1, I must have grabbed something wrong. B1 is S, B7 is D. Oh, you know what I did? I up here I've got D1 instead of ND1. That's better. Yes. Anyway, so this is saying the call price is approximately 7,633. Now, here's an interesting note. Look up here. The intrinsic value, this call option is S minus X. In other words, if this was an American option and I exercised it right now, I would get a payoff of $2. Okay. This is the payoff that would be received if the option were an American option and could be exercised today. Now, if you notice the actual price, 7.633. So what this means then is that the rest is the time value of the option. Okay, so the reason why it's so high is because this has a full year to maturity. That's a long time for an option. That means what you're paying for is the possibility that the price of the stock will continue to rise and that you'll make even more money with your option. Time value reflects possibility that stock price will continue to rise and provide a higher payoff to the option in the future. Note, the time value of the option will be exactly 0 on the expiration date of the option. At any time prior to that, the time value will be positive. Okay, now put call parity. Now we haven't really discussed it yet, but since the formula is sitting right here, why don't we just go ahead and fill it in? Yeah, we'll get to that in a bit. We want to explain what it is. Here's the formula. We want to understand how and why it works. Okay, so we're going to have this call price plus, again, X times EXP minus R times T. Oops. Minus the stock price. It's approximately $4.64. It's rounded to. That's good. So the call and the put price are usually not equal to, very rarely are they equal to each other. So since this option is $2 in the money, the call is $2 in the money. The put is $2 out of the money. That's why the call is more expensive than the put. Okay. So the call is $2 in the money and the put is $2 out of the money. Therefore, call is more expensive than the put. Okay. So now what we have to ask ourselves is, well, wait a minute. What is this put call parity conditional about? Why is this appropriate? How do we know that this is the correct price for that put? In order to do that, what I've done is I've added it here. It got left out of the slides for some reason. I'll probably have to put it back, but I wanted you to see this properly. The proof of why this condition holds. Now it's a table that we're setting up here. It's not like we're proving that a function is continuous or something like that. We're proving that, well, let me give you a little bit of sense of what we're trying to prove here. This is the logic behind this proof. Where should I put this? Well, actually, I'll throw it on here onto the spreadsheet. Why does the call parity condition hold? Well, the underlying logic behind this call parity condition is that if two portfolios are guaranteed to have the same cash flows at a point in the future, and their prices must be equal today to prevent an arbitrage opportunity from arising. How is that? Because suppose that portfolio A is a let's see, what kind of example could I make up real quickly? Let's just say that somehow, if they consist of treasury securities whose value will be $100,000 on July 1st, let's say. All right. They've got a bunch of different treasury securities that are all, the way they're structured is they're both going to have the same value on July 1st. Okay, guaranteed because there's no default risk. If portfolio A is cheaper than B, an investor could buy A, sell portfolio B, and collect the difference. On July 1st, the investor will collect $100,000 from portfolio A because he owns it, and use this to pay the buyer of portfolio B. So the net cash flows Zero. Okay. So in other words, the investor earns a positive cash flow today and has no outflows in the future. In other words, there's no cash flows at all. And on July 1st, there are two of them, but they exactly offset each other. And then after that, there's no more cash flows at all. So therefore, this is an arbitrage. Meaning I just earn risk-free profits that I should not have been able to earn if the portfolios were priced correctly. Ah, so that's exactly what's going on behind the scenes with the book call parity condition. As long as we choose the portfolios correctly, we can prove that there's going to, on the maturity date of these options, calls and puts, the two portfolios we're about to set up have to have the same cash flows. All right, so once that's done, what we're going to do is see the a more, let's say, sophisticated version of Black-Scholes. Robert Merton, after this paper came out, he wrote another series of papers in which he explained how the Black-Scholes model could be adapted to price options on other securities besides those that do not provide cash flows. And it's not a very complex extension, but we want to look at it and see how it's different. And so by this, by the way, really opened the doors to all kinds of options being traded in the marketplace because suddenly it became possible to price any European option in the market. It took a bit longer to come up with a model for American options, but that, really by that time was only like 1976. And then the sky was the limit with options trading. Everybody could essentially price any option. And so the activity in the markets grew dramatically. So I'll tell you what, let's do this. I think what we can do is we'll save the proof, which is right here. We'll go through it very carefully and slowly. And then we're going to see how this advanced version, which in Hull's book, he calls it the Black-Scholes-Merton model. And you'll see it's a very simple extension. It's not very different. And then we'll do that in Excel. And then I'll show you how to get this going in VBA. And then when that's done, we're going to step into the world of American pricing options, American option pricing models, that is. Yeah, actually, I'll tell you what, this section 6 is a look at these Greeks, which are risk measures. I will go through that, but it won't take that long. This is what I'm really after, this binomial option pricing model. This is a really huge development because this is where we are now suddenly able to price American options. So the Greeks are interesting, and we'll go through that. But the crown jewel, I guess, of the latter half of this course is this binomial option pricing model, because this is what makes it possible to price American options. Now, there's other alternative approaches to doing this. There's after the binomial option pricing model was introduced in 1976, we have this trinomial model coming along. And then we have Monte Carlo simulation being applied to option pricing. But the thing about Monte Carlo is it's really best suited for what we call exotic options, the really bizarre ones with strange features, but it's good to know what this is all about. So anyway, we have a lot of very important things coming up. So next time we'll discuss the proof of the put call parity condition. We'll quickly run through the Black-Scholes-Merton model. We'll get through the Greeks, and then we get to do the binomial option pricing model, which will be very exciting. Also, within that discussion is a closer look at the foundations of all option pricing models. And so it's very interesting and very important. So anyway, I'll see you all next time.